That was just an introductory video regarding the Starship program. That was all real, no CGI there. What we're aiming to develop with Starship is a generalized means of transporting large amounts of mass or people, but just in general, large amounts of mass anywhere in the solar system. The idea behind this is to have the first fully and rapidly reusable rocket, which is that's really the holy grail of rocketry. If you can have a fully and rapidly reusable rocket, orbital rocket, then the cost of transport of a ton to orbit drops by about 2 orders of magnitude, maybe better. So, just as it would for really any mode of transport, if you say had aircraft or cars that were not reusable, you would see very little use of aircraft and cars because you'd have to buy a new aircraft every time you went somewhere. And if you traveled somewhere in a car that was single use, you'd have to obviously tow a small car behind you just for the return journey. So I think this is quite profound. If we are successful, and at least from a design standpoint, it appears to be, all of the calculations close for having a fully reusable 100-ton to low Earth orbit capability. The vehicle is very big. So one of the things that helps with reusability is scale, because, for example, the electronics that control the brain of the vehicle, if you will, does not actually get any heavier if it is a big vehicle or a small vehicle. So things like avionics and control, inertial measurement, sensors and whatnot become round down to basically almost no percentage of the mass for a big vehicle. Whereas for a small vehicle, obviously that would be much more of an issue. So scale certainly helps. And then we're using the most advanced engine cycle, which from a physics standpoint is the best. You can extract the most amount of momentum for a given amount of fuel or propellant, which is a full flow gas staged combustion engine. That's the Raptor engine. There are currently 29 of those on the base of the booster. We'll be expanding that to 33. At 33 engines and with the Raptor 2, we'll be doing about 7,700 metric ton force of thrust on liftoff. So it's about 2.2, 2.3 times the thrust of a Saturn V. So it's really a very big vehicle. It's the biggest rocket ever designed, and we're close to our initial launch, our initial orbital launch. We've done several suborbital flights and have been able to land the vehicle successfully. The first orbital flight we're hoping to do in January. So we've completed the first orbital booster and first orbital ship, and we'll be complete with the launch pad and launch tower later this month, and then we'll do a bunch of tests in December and hopefully launch in January. There's a lot of risk associated with this first launch, so I would not say that it is likely to be successful, but I think we'll make a lot of progress. And then we've also built a factory for making a lot of these vehicles. So this is not a case of just one or two. We're aiming to make a great many. Ultimately, I think in order for life to become multi-planetary, we'll need maybe 1,000 ships or something like that. But the overarching goal of SpaceX has been to advance space technology such that humanity can become a multi-planet species and ultimately a spacefaring civilization, and to make true the things that we read about in science fiction and have them not always be fiction. I think this is actually quite important. Well, long term, it's essential for preserving the light of consciousness. Eventually, something will happen to Earth, hopefully not soon, but either natural or man-made, that would cause the end of civilization. So the probable lifespan of civilization is much greater if we are a multi-planet species, and ultimately even go beyond our solar system. But the first step is being multi-planet, Mars being the only realistic option for that. So I think from a standpoint of, yeah, like I said, from a standpoint of preserving the light of consciousness, and which I think we should regard as fragile, I think it's extremely important that we try to become a multi-planet species as quickly as possible. Obviously, along the way, we will learn a great deal about the nature of the universe. And it will be possible to have many more space-based experiments if you have a very large vehicle capable of transporting things to orbit or the moon or anywhere at 100 times less than it currently costs. So it offers sort of profound possibilities, and I think this, there's a fundamental juncture in the history of really any civilization on a single planet, which is, do you get to the second planet or do you not? I propose we do. And I think we should do it as soon as possible. The window of this opportunity is opened now for the first time in the 4.5 billion year history of Earth. It may be open for a long time, or it may be open for a short time. And I think we should, be hasty so that just in case it's only open for a short time. Yeah, so like I said, I think this is very important for the long-term preservation of the light of consciousness. And of course, we'll naturally, we'll learn a lot of science and develop a lot of technology along the way. So that's what Starship's all about. We have an interesting project that we're working with Sol Perlmutter at Berkeley on, which is to have a really big telescope. This is taking a ground-based lens that was intended for a ground-based telescope and creating a space-based telescope with it. So that could be, I think, pretty interesting, and we'd love to do other things as well. So yeah, and I think people may know that NASA has selected Starship for the transport of astronauts to the lunar surface. So we look forward to doing that for NASA. And then I think, it really could be, it has the ability, because of the mass transport capabilities of transporting enough mass and people to the moon, to actually have a permanently occupied, I think, base on the moon. Much as we have like a permanently occupied base at Antarctica, we could have a sort of a moon research station, which I think would be amazing. So yeah, I think, anyway, this is a very profound vehicle, and nothing really like it is being developed, and I don't think anything quite like it has been even proposed. But it has the potential to affect human destiny in a very profound way. So I'm happy to answer any questions. I'm not sure quite what you'd like to know, so maybe real-time questions are the best way to address what people may be thinking.
Terrific. Thank you so much, Elon. From our board members, please raise your hands for questions. And our first question will come from Louis DeMauro.
I think you may be on mute.
Yeah, still muted. There you go.
It's just saying thank you for that. It's a rather big vision. I wonder, in order to achieve this goal that you painted, what type of international collaboration do you see to get this done? And, what are the possibilities of actually pulling that off?
Well, we're not assuming any international collaboration. We're building this thing right now, and we're really building it from internal funds. NASA is providing some support because they intend to use Starship for transporting astronauts to the surface of the moon. But this has really been an internally funded effort. Probably, I don't know, at least 90% internally funded thus far, and we expect to reach orbit. Probably, I don't know if we'll get there on the first attempt, but I'm confident we'll get there next year, and we intend to have a high flight rate next year. It's difficult for us to actually have international involvement because of ITAR. So I'm not sure. I don't really see anyone outside the US who is building some part of what we need. We're just doing it.
It's great. Wonderful answer. Next question will come from Adam Burrows.
A fascinating vision. I don't know where to begin, but I will ask just a technical question. It was surprising to many that I believe you chose a stainless steel for the vehicle. I could be wrong, but what were the technical and engineering reasons for that? And don't stint on the details.
Sure. That's I think a very interesting question, because to a lot of people intuitively they would think of steel as being heavy, and rockets need to be light. So, well, that seems a pretty odd choice, picking a heavy sounding thing for rockets, especially orbital rockets that need to be very light. I mean, the nature of Earth's gravity being quite strong and a dense atmosphere means that you really have to have an incredibly good propellant mass percentage, and you have to have very efficient engines to get anything to orbit at all. So then why steel? So we started off with an advanced composite. So intuitively, if you ask people who understand materials, they will say we want to make something incredibly light. They'll say probably you want to use state-of-the-art carbon fiber composite. That's usually what they'll say, and that's what we started out with, which was really a very advanced carbon fiber. Actually, it was only made in very small quantities. It cost $130 per kilogram, so it was very expensive material. And there are some challenges if you want to make the primary structure out of carbon fiber, which is that you've got to contain cryogenic fluid, and you need gas in sort of what's called ullage gas, pressurization gas, to pressurize the propellants in the main tanks and feed the engine turbopumps with a given inlet pressure. So if you have a carbon fiber tank, because it tends to be porous, and also potentially flammable when subject to warm gaseous pure oxygen, because our vehicle is autogenously pressurized. So the oxygen tank is pressurized with gaseous oxygen, and the fuel tank is pressurized with gaseous methane. The resin and the carbon in the carbon fiber is potentially flammable with hot, pure oxygen gas. So you'd have to have some kind of liner. So when you look at the full mass and complexity of a carbon fiber system, you start having things that reduce the mass efficiency of carbon fiber, such as having an inert liner and being worried about gas permeating through the carbon fiber and that kind of thing. So but it still would be it's still an okay choice. However, we were having a lot of trouble making progress with the carbon fiber, because this is a 9-meter diameter rocket, and so you're wrapping carbon fiber with typically, in this case, 60 to 120 plies, depending upon where you are in the tank, and you have to get all of those wrappings accurate and not leave bubbles or separator sheets or all the things that typically happen, or you've got to scrap the whole thing. And then you've got to get good mass properties, put it in an autoclave and put it under a lot of pressure. And then you need a gigantic autoclave because it's a 9-meter diameter with a 70-meter long boost stage. So this is autoclave from hell. And we just weren't making rapid progress with this material. So then the next thing, the other two materials worth considering are a high strength form of aluminum or aluminium, or potentially steel. So for Falcon 9, we use aluminum lithium, which is the highest strength to weight aluminum alloy that you could use. Very difficult to weld, but that's what we use for the primary structure of Falcon 9. Then, but the problem is it's very difficult to weld. You need to do friction stir welding, and also the material cost is quite high. So, that's sort of material cost, arguably on the sort of $40 a kilogram level, and like very difficult to weld. But then there's steel. Now, the interesting thing about 300 series stainless steel is that its properties at cryogenic temperatures, its strength properties increase dramatically. So if you were to look at the material properties at room temperature, you'd be like, oh, it's not that great. But now go look at the temperature properties at liquid oxygen temperature. Oh, actually much stronger. Also no meaningful increase in brittleness. So it still has high toughness at cryogenic temperatures. It is much stronger, depending on how cold you go, up to twice as strong. And then and then if you can also cold work it. So you get if you go sort of full hard cold work and do the final bit of cold work at cryogenic temperatures, you get outstanding strength properties, which are roughly equal to an advanced carbon fiber. And this is, and in our case for Starship, both the fuel and the oxygen are cryogenic. So this helps a lot. Whereas for Falcon 9, you use cryogenic oxygen, but kind of room temperature kerosene fuel. So anyway, we're both. This is quite a long explanation. Hopefully interesting. If both fuel and oxygen fuel and oxidizer are cryogenic, now you get the strength properties in the primary structure of both tanks. So both are very strong, very tough and resilient, also very easy to weld stainless steel. And we started off with stainless steel 301. That did have some fracture toughness issues at cryogenic temperatures. We switched to 304, and now we developed our own alloy, which is 30X, which is better than either 301 or 304. Anyway, so now stainless steel only costs about $4 a kilogram. So we went from $130 a kilogram advanced carbon fiber to $4 a kilogram stainless steel, from 120 plies to 1 ply. It's just coil from the mill, and basically the same strength, and very high toughness and resilience. And don't even need to paint it, which is great. So paint is, paint on a big vehicle weighs many tons, and it's quite difficult to paint big things. So, but now there's another advantage. So obviously you can tell I'm a huge fan of stainless steel. Stainless steel and I should get a room or something. In making the vehicle reusable, so now it's coming in very hot. So the ship is coming in at hypersonic velocities, coming sort of kind of like a Mach 25 entry velocity. So this would just obviously just melt it. But if you've got steel, your melting point is much better, higher than aluminum, and you can handle much better temperatures than carbon fiber, because the resin tends to have problems. Like you can basically go, anything much above, say, 200 Celsius, or for carbon fiber or aluminum, is you start falling off a cliff from a strength standpoint. But for steel, you go 800, and it's fine. Even 1,000 can be fine. So for the ship, this means that the heat shield mass is significantly reduced, because the heat shield mass is determined by the temperature on the back of the tile that then transmits to the hull. So the hull, if the hull is steel, you can have thin heat shield tiles, whereas if the hull is carbon fiber or aluminum, you have to have thick heat shield tiles. And you also need no heat shielding at all on the leeward side of the ship. So it is actually lighter than the most advanced carbon fiber vehicle.
Yeah, I'm very surprised at that, but that was very, very interesting. I appreciate your long disquisition on this, and I thought that the steel substituting for aluminum on re-entry made some sort of sense. I didn't realize any of the other stuff.
Yeah, it ends up being the right thing, and then it's just and it's the cost is ridiculously low. It's like $4 a kilogram. Even for the special alloy that we're developing, although it requires like a mill run, it's not using anything super exotic. We might throw a little exotic spicy something in there, but it's a small, it's it's gonna be like 0.2%. So it's still gonna be like maybe $4 a kilogram, maybe $4.50. And then it's just very easy to weld. Yeah, I love it. It's great. And then if we want to just add something to, if you want to, it's easy to repair. It's, if you want to, add a sort of something to carry some wiring or plumbing or whatever, you can just weld it right on. It's super easy. It's great.
Thank you. I very much appreciate that.
It's a high tech, low tech. Wonderful.
Yeah.
Our next question will come from Howard Singer. Elon.
Hello, I started my science career watching Captain Video and reading Isaac Asimov, and you've made all that fiction real, so thank you very much. My question is, what are you doing for radiation protection for the crews? And if you have you explored the need for forecasts of the space weather conditions or the space weather environment?
Sure. Well, I think there is, there's always some risk going into deep space, and we definitely wouldn't want to be traveling when there's like intense solar storms or anything like that. For going to the moon, like obviously, the United States has done that before, and it would be great to go back and great to have a permanent base where, if the costs are good enough, where we could have like a significant science contingent actually, on the base, permanently occupied. It would be epic. But once you're on the moon, of course, you're protected by the moon below you, and then you can put a lot of lunar regolith on top of whatever the research station roof would be. So once you're there, easy to protect. On the way, we'll have to check the weather report. And for Mars, it's going to be trickier. Obviously we don't have all the answers here, but and there may be some clever ways to reduce radiation effects. But I don't think they're insurmountable.
All righty, thanks. Our next question comes from Margie Kivelson.
So I'm an enthusiast for the outer planets, and SpaceX is giving the Europa Clipper a lift out to Jupiter. I wondered if you have comments on other missions that you would like to enhance by providing big lifts.
Sure. Actually, we're really excited and honored to be flying the Clipper mission. I think there could be some incredibly exciting things to discover. Hopefully, are under Europa. It seems like probably the best place for some strange life. So hopefully we find some really cool things. So yeah, I can't wait to launch the Clipper, and that'll be on a Falcon Heavy currently. With the Starship, we could, like, the great thing about Starship is it really should enable us to send very big things, and also to send them fast, and like need much less in the way of sort of planetary gravity assists and that kind of thing. So especially if we could build a propellant generation on the moon, then we could really send something with very high delta V. And if we have a base on Mars with high delta V, now you can basically planet hop from Mars to maybe Ceres, to maybe one of the moons of Jupiter, and ultimately all the way to the outer solar system. Basically, any place we can put the gas station, that gives us another whole leap forward. So ultimately, Starship is designed to be a generalized transport mechanism for the greater solar system. And so it's really whatever you can imagine being, if you could get, 100-ton object to the surface of Europa, there's a lot more you can do than with a smaller object. Yeah, I think it's very exciting. Obviously, we still have a lot to prove, but architecturally, it is capable of transporting kind of almost any arbitrary mass to any solid surface in the solar system.
Wow, terrific. Thanks. And Margie is actually leading the team building the magnetometer that you will be taking to Europa on the Clipper. Our next question comes from Steve Mackwell.
Hi, Elon. Thanks so much for your presentation. I was wondering, what are your kind of plans for humans to Mars in terms of timescales, and are you going to send folks there for kind of a shorter stay, or you think a longer stay and bring them back, at least initially?
I'm not sure. I think so. The first thing we'd want to do is confirm that we can land the ship safely on Mars, and so that might be, we'd want to probably land 2 or 3, I think, before sending people, and just confirm that we can land safely. So and actually on those missions we could obviously put a lot of scientific instrumentation. That I would recommend putting the lower cost scientific mission stuff on the first mission, but we'll certainly have propulsive landing very reliable on Earth, as we've been able to achieve with the Falcon 9 booster. It's now, knock on wood, so it's no longer, it's quite normal for the rocket to land safely, and we'll do the same with Starship, and then. I'm not sure quite what would happen. I mean, we might be working with NASA, or maybe NASA and other other countries to send people to Mars. But I view this very much as what set of actions can we take that maximize the probability that the future is good for civilization? Like what are sort of like civilizational risks that we can potentially mitigate? I just think being a multi-planet species is a tremendous risk mitigation for human civilization. As we know, eventually the Earth will become, if you wait long enough, Earth will become uninhabitable. So in the long run, we're obviously all dead. but I think the technology that we develop in traveling from Earth to Mars, I think will be just a very powerful forcing function for the improvement of space transport. Like the initial boats that crossed the Atlantic and crossed the Pacific back in the sailing days were really terrible. So they were often just plain sink, but once there was a reason to do large amounts of ocean trade, the sailing ships, the wooden sailing ships, got dramatically better, and so, but you kind of have to have that forcing function. So that's what I think will happen, and we'll get much better at space transport. And I think this will also be very important if if there's like a potential Earth collision event from some comet or something like that. The asteroids we can predict fairly well, obviously, but there's this massive cloud of comets out there that we don't know the situation. And they come in pretty fast. So there's always some risk of a comet like taking out a continent. There's this place like they talk a lot about extinction events where almost all life was destroyed on Earth, but they don't talk that much about the ones where, well, it was just a continent. There's plenty of sort of continent level extinction events that have occurred in the fossil record, and they're like really so common as to really not really generate much attention. But if we've got large rockets that could potentially do something about that, then that could be, that could at one day save billions of people. But we've got to have big rockets and much more advanced space technology in order to protect against a comet coming in from far away.
Okay, thank you so much.
Terrific. Thanks, Elon. Our next question will come from Harlan Spence.
Elon, thank you for sharing your time and your vision with us. I had a question about looking back the history of exploration, human exploration, as we ventured from one place to another. Scientific discovery has always been an element of that. And you've shared a little bit about some opportunities there. But I was hoping you could share a little bit more. When you think about the aspects of scientific discovery that will accompany becoming a multi-planet species, what are the kinds of things that you're thinking about in terms of what we would discover along the way?
Well, I think being able to really, have heavy-duty science research on the moon and on Mars, where you could really just go anywhere you want, drill core samples anywhere you want. I think we'd learn a tremendous amount as compared to having to send fairly small vehicles with limited scientific instrumentation, which is what we currently do for Mars and the moon. So just having people there who can dynamically decide what they're going to do, and really being able to analyze the whole history of the planet, I think we'll learn a tremendous amount. And that would obviously extend over time through at least the greater solar system. I studied physics because I was just trying to find out what's the universe all about? How does it work? Where did it come from? Why are we here? I actually kind of got sort of depressed at one point because I was like, man, this doesn't seem to be any meaning to life. It just seems to be like, and then I made the mistake of like reading the German philosophers as a teenager. That made it was quite depressing. But then I read Douglas Adams' Hitchhiker's Guide to the Galaxy, which is really a book in philosophy disguised as humor. And he makes the point that the question is harder than the answer, and really basically the answer is the universe, and we kind of need to figure out like what questions to ask about the answer to that is the universe. And that's the question is the hard part, and then the answer is easier by comparison. So I'm like, I don't know, like why are we here? How do we get here? Is this real? Is this a simulation or something? At least if we go to these other planets, we'll make the simulators work harder and have to buy more computers to run the simulation or something. I think it's and if we are able to at least be like a multi-planet species within the our solar system, then hopefully we can develop the technology to send probes to other star systems, and eventually maybe send people, although that's tough, but we can certainly send robots to robot probes to all the nearby star systems, and try to figure out what's the meaning of life and what's going on, and are there any aliens out there? Where are the aliens? They're so soft.
Yeah. Thank you, Elon.
Sorry, go ahead.
Do you have time for a question or two more?
Yeah, as much time as you like.
Oh, wonderful. All right. I do have one question from a board chair, and it's this. One aspect of SpaceX that has distinguished it from the previous organizations has been its willingness to embrace failure as a development tool. When do you think you will be able to start selling Starship launches at prices significantly less expensive than Falcon 9, say 5 to 10 times less?
Sure. Actually, I think it's not that far away. I think probably 2 years from now. Our rate of progress on Starship is very rapid, like I said, we're actually getting ready to do our first local orbital launch attempt within the next few months. We're expecting our license approval from the FAA around the end of this year, and then so that probably means a launch attempt in January or perhaps February, and then we're actually building the factory to make lots of Starships and make lots of engines in parallel. So there will be many vehicles. The engine build rate is currently the biggest constraint on how many vehicles we can make, because there are currently 29 engines on the booster, and there will be 33 even at a higher thrust level. That means, yeah, so 33 engines per booster, and these are big engines. These are the Raptor 2 is a roughly 240-ton thrust engine. So we're talking like 500,000 or 600,000 pound thrust engines. So really quite intense. In fact, I'd say that building the production system for Starship is much harder than the design of the Starship itself. But we have that in progress, and we intend to do hopefully a dozen launches next year, maybe more. And if we're successful with it being fully reusable, it means that we build up the fleet, just as we are with the Falcon 9 and the Falcon 9 booster, which is reused. We lose the upper stage every time, but we almost always recover the booster. So basically, we intend to complete like the test flight program next year, which means that it's probably ready for valuable payloads that are not kind of in the test, not for testing basically, but actual real payloads in 2023. So quite soon.
Great, thank you so much.
All right.
Next question from Ned Wright. Ned, I think you're still muted. Won't we all be glad when we don't say that all the time?
Yeah, so it's you have to preserve cryogenic propellant for 6 to 8 months to actually be able to land on Mars. And so I wonder what your plan is for that.
So the landing propellant for Mars would be in separate header tanks. So these would be spherical header tanks. For Mars, there would probably be, they might be contained inside the main tanks, or they would be up in the cargo section, but well insulated. So you would obviously have to have extremely well insulated header tanks for landing that are not the main tanks. So that's what we'd have for Mars.
Great, thanks. Riza Wexler is the next question.
Yeah, so changing topic to something that's happening before we have the possibility to be a multi-planet species. I also study the universe, and I'm trying to understand how it works and how it got here. And as you know, the satellite constellations from Starlink and other sources are already having a huge impact on astronomical observations. And this is really going to significantly limit the science potential of the next generation of observatories if we don't have a course shift. So what role do you expect SpaceX to play in working with astronomers and regulatory agencies to mitigate this?
Well, SpaceX already works with regulatory agencies and with the astronomers, generally what we see is the telescope that is perhaps most sensitive to this is Vera Rubin. We work directly with the Vera Rubin team to make sure that their observations will not be affected by Starlink satellites. And my understanding is at this point they are comfortable that it will not be an interference for Vera Rubin. They have there's a slight risk of capacitive coupling between some of the sensors there, but which can create ambiguity. But we're confident that we can work around that.
Great, thanks. Our next question comes from John Karras.
Elon, thanks for all your time today. Appreciate it. Kind of going back to a prior question about long-term storage or cryogenics for whatever mission, but I realize, or I believe that your architecture for Starship to go beyond low Earth orbit to go to the moon has, cryofluid transfers and things like that. And, long-term cryofluids, cryofluid storage, low boil off.
Oh, yeah. Those are not easy problems.
No. And so not easy problems. So the question I have for you is what are your plans to mature that technology, but before you have to rely on it to go to the moon, like in a year or two?
Well, so, there's a lot of ways to address it. By having launching one vehicle that is very well insulated, but does not return to Earth, effectively a propellant depot. So if you take a Starship, and you take the heat shielding off and replace that with thermal insulation, like a multi-layer insulation that's just very, very good at keeping things cold, then you could have one ship up there that it effectively just turns into a propellant depot, and then you send tankers up there to dock and transfer propellant. And so it should be able to be there for a while, and then whatever ship you want to go to the moon, you go up and dock with the depot, transfer propellant, and off you go. So that's a rough plan. We're pretty good at docking at this point. We've docked with the space station a couple dozen times, and the space station is a very difficult thing to dock with because we don't control both sides of it, so that is very challenging docking. Whereas docking with our own vehicle is comparatively easier.
Yeah, but both of these technologies have really only been demonstrated on very, very small scale. So your scale is a lot larger, and I think poses other problems. So good luck in solving those.
Yeah, no, I don't think we'll just sort of it's not exactly a walk in the park. So I think this is hard, but it is necessary, and it's the only way, at least with that I'm familiar with current physics, to actually make things work. And then obviously, aerial refueling is used quite a lot with aircraft. And so this is taking that concept and just doing it in orbit. So we know that success is one of the possible outcomes. We're not breaking any physics. Physics is the law and everything else is a recommendation. So, but just because it's at least in the set of possible success is at least in the set of possible outcomes. Yeah.
Great. Thanks very much. Next question will come from Amanda Hendricks.
Hi there. So I'm a co-chair of the Committee on Planetary Protection, and our committee is concerned with preserving the validity of future astrobiological experiments on Mars and other places in the solar system.
Yep.
Searches for life, extinct or extant. And I wonder if you can comment on SpaceX's planetary protection plans for Mars.
Sure. Well, first of all, it's not like we'll be launching to Mars really soon. Mars is a ways off. And the, but there is, fundamentally a choice to be made, which is, are we going to try to be a multi-planet species? Which would mean like at least in one spot on Mars that there is human biology, like that we will be, we're pretty hard to avoid no biology if you send humans there. We're biological creatures. But I don't think this is going to invalidate research on the rest of the planet. I mean, Mars is a big planet, and so and there've been rocks that have been knocked off of Earth and landed on Mars and that kind of thing. So, but yeah, I think you wouldn't want to sort of spread biological debris all over Mars, but I think we will have to put at least somewhere if there are people going there, at least in one spot, and then just make sure we try to contain that and not have it sort of spread around. Yeah, and I guess it's same for the moon and other places.
Thanks.
Thank you, Elon. We'll just take a question or two more. Next question from Larry Paxton.
Hi, thanks for your time. I have a question that was engendered by a remark you made in passing that I think is very interesting, which is where you said that there's a window of opportunity for us to get off the planet. And the question that occurred to me was, you followed that up with saying that you didn't know how long that window of opportunity would be open.
Yeah.
And there, you mentioned in passing, of course, the traditional things like, exogenous forces like cometary impact or a near-Earth object. But I was wondering, with all these compelling reasons for us to get off the planet, and including the compelling reason to have another refuge for the human race, what do you see as the biggest threats? And in particular, we have a wide range of expertise here. We've been talking about some of the problems that we think are the most important that are unresolved yet. I just wonder what you felt were the most important issues for us as a human race.
Yeah, I mean, in general, I've thought about this quite a lot, which is not to say that I've thought about it correctly, but I've thought about it a lot. And the one of the bigger risks on Earth would be, that we need to transition to sustainable energy. Even if one discounts the CO2 capacity of the oceans and atmosphere, eventually we will run out of hydrocarbons to burn, and so we need something that's long-term sustainable. So that's sort of I kind of split my time between Tesla and SpaceX, and so Tesla's trying to accelerate the advent of sustainable energy, and that's to mitigate the risk on Earth. And then SpaceX is intended to mitigate like longer term risks that could potentially extinguish consciousness as we know it. I mean, we got the sort of delicate candle of consciousness sort of flickering in the darkness here. And I don't know if you guys have seen any evidence of aliens, but I sure haven't. I get asked that a lot. So, I mean, I think the Fermi paradox is just an incredibly interesting question. And I'm not sure who said it, but there appear to be, if there's either a lot of aliens or none, and equally, those answers are equally terrifying. So anyway, so I think, but with respect to nearer term risks on Earth, obviously sustainable energy and potential nonlinearities in the CO2 ppm in the atmosphere are a concern. If we start doing things like melting the Siberian tundra and that kind of thing. I'm probably less alarmist than most on climate change. I'd put myself in the moderate category on climate change. I just think it's the amount of inertia associated with the hydrocarbon economy is so gigantic that it will require a long time to make that transition. And so it's probably better to start it sooner rather than later. And that's why I describe the fundamental good of Tesla as the degree to which it accelerates the advent of sustainable energy. It will happen, I think, anyway, but faster is better. Then as for risks on Earth, I mean, there's always good old nuclear Armageddon, that's still one of the things. That's not out of the question. There's still a lot of nuclear missiles pointed all at us in the US and many parts of the world. I don't know what quite that risk is, but it's not zero. I think there's maybe some counterintuitive risks or that people don't put that much attention on. If you look at the birth rate trends, the birth rate trends are very negative. And in many countries are seeing population decline with no end in sight. So I think there's, I think the very low birth rate, I think, is actually quite a significant risk, but an underappreciated one. Yeah. And for population prediction, I would recommend taking things like the number of babies born last year and just multiplying that by the probable lifespan. And if you do that, I think you'll see numbers that are very, very bad for future population, and with an inverted demographic pyramid. So you've got a lot more older people and then fewer middle-aged people, and then eventually just very few youngsters. And this will necessarily lead to resources being applied to taking care of the elderly instead of advancing science or advancing civilization. I'm quite worried about that one because I see no reversal of the trend. That would, civilization will die with a bang or a whimper. That would be dying with a whimper. Then there's obviously, of course, a pandemic that's like COVID, but which has a much higher mortality, sort of a long, high contagion, highly contagious, long incubation period, high mortality type of pandemic. That's clearly a risk. AI is, I think, maybe more of a risk than people realize. Ironically, the smart people tend to think AI is less of a risk because they think that they're so smart, but actually we're just humans and we're quite dumb. It's amazing we got this far, frankly. So if you see the advancement of AI, it's clear that AI will exceed human intelligence in every way if these trends continue. And the list of things that the human mind can do better than AI is less and less every year. So, hopefully that AI is coupled to human will, but it might not be. The long-term goal of Neuralink is to achieve sort of better symbiosis with AI and with the kind of human mind. In the short term, Neuralink, I think, will help solve a lot of brain injuries and diseases and spinal injuries and that kind of thing. But long term, because one of the things that I'm getting quite esoteric here, but we're already a cyborg, really, in the sense that our phones and computers are an extension of ourselves, and you could say we arguably have the primitive kind of limbic system, the cortex, the higher thinking, and then we've got a tertiary layer, which is silicon in the form of our computers and phones and everything. We have already somewhat merged with computers, but the issue we have is the communication rate, the bandwidth with the computers is low, especially output. If our output is 2 thumbs, that's, we're talking maybe 10 bits per second or something like that. Or maybe 100 best case. It's a very slow output. And as the intelligence of the computer grows, if that communication link remains very tiny, I think we will necessarily decouple from computers just because our rate of communication is very slow. And so if we can solve the I/O bandwidth question and by, increase it by 1,000 or more, maybe 1 million, then you could have human machine symbiosis that is much better. I mean, that's at least one approach. Let's see, what else is there? I mean, religious extremism, if that becomes, if that grows over time, religious extremism is certainly a threat to advancement of science. So depending on how far that goes, that could be an issue. What do you think?
Yeah.
I think I will only add, I think that this is a fundamental question because, as you said, the Fermi paradox, should either be a tremendous number of alien civilizations, or there is some gate that so many civilizations have failed to get past. And the question is, are we going to fail to get past that gate as well?
The great filters. Yeah. So I think at least one of the great filters is, does a civilization become multi-planetary or not?
Yes.
If a civilization does not become multi-planetary, then eventually the sun's going to expand and boil the ocean, and that's game over. So, and actually, if you think about it from a percentage standpoint, if Earth's been around 4.5 billion years, and it took us 4.5 billion years to get this far, well, it may be as soon as another 500 million years, and the sun might have expanded enough by that time to boil the oceans potentially. If it's not 500 million years, it's not much beyond that. Which is basically means that if it took 10% longer for civilization to evolve, it would never have evolved.
Right. So there's an interesting one. Elon, do you have time for one more question? Wonderful. All right. Jill Dahlberg, please.
So let me just say, I feel lucky that you are here. So thank you. And not just here in our panel. You're very inspiring. My question is mundane. You're going to have these rockets. They're going to go up and they're going to go to two places that are going to need energy. The Earth needs a lot of energy as well. Yeah. So what are your plans for making energy? I'm thinking space-based solar power or something like that. Does your company have plans for proliferating energy systems you're going to need?
Well, Tesla does do solar power, and solar is actually, there's quite an amazing amount of energy that reaches us from the sun. Really, when you think about it, Earth is almost entirely solar powered. If it were not for the sun, we would be a frozen dark ice ball at 3 degrees Kelvin. So apart, keeping us warm and not super cold and frozen and dark is pretty helpful. And then almost the entire ecosystem is solar powered. Plants are a solar powered chemical reaction, and apart from chemotrophs at the bottom of the ocean, it's basically everything's solar powered. So we're really talking about just like a little bit of incremental power from the sun being used to power civilization. As a sort of good rule of thumb is because you get about a kilowatt per square meter of solar energy. So then in a square kilometer, there's 1 million square meters. So now you've got a gigawatt of solar energy per square kilometer. And so if you've got like 25% efficient panels, and there are maybe 80% of the area is panel of then you've got like basically 200 megawatts per square kilometer of solar power. And so then if you say, well, okay, how much, then you really won't need a very large area to power the entire United States with solar. Like a little corner of Utah or Texas, obviously you prefer it to be distributed, but you can just say like, okay, how much is actually needed to power the US? And it's, somewhere between a square that's roughly 150 to 200 kilometers on a side will power the entire United States. So it's really clearly no problem to power civilization with with solar. And then of course there's wind, and I'm actually pro nuclear, fission wise, and there's also hydro and geothermal. So I think we will solve Earth's energy needs, and they are being solved. If you look at the growth of wind power and solar power it's really has a very high growth rate. It needs to be paired with batteries in order to, because the intermittency of wind and solar. But the combination of solar plus battery can completely solve all of Earth's energy needs. In fact, for satellites that are in orbit, that's all they use is solar panels and a battery. And what is Earth but a large satellite? Sorry, I think you're on mute.
Do you
I just
want to
want
follow up?
Yeah, I was thinking something more grandiose, like a space-based solar power system, but you have a good argument. You would just use solar on Earth, battery, and plethorate. I like that. Thank you.
It works great. Because if we think civilization uses a lot of energy, but it's actually very tiny compared to the amount of solar energy that reaches the Earth every day. Yeah, it's just there. I get asked a lot about fusion, and in my opinion, like if you just make a very large thing of magnetically confined fusion, you could absolutely make it work. I don't think any really major breakthroughs needed to make fusion work, but I think it's unnecessary to make fusion work because we've got a giant fusion reactor in the sky that just shows up every day and doesn't require any maintenance. So it's a low maintenance fusion reactor, shows up every day. So if we just catch the energy from, catch it, it's just keep lobbing all this energy at us, just catch it with the photovoltaics and store it in the batteries, and that'll solve for everything basically. Yeah, we need a lot of batteries, but there's also, like, the next question might be, do we face some materials limitation with batteries? And the answer is definitely not. I think the vast majority of stationary storage will use an iron cathode lithium-ion battery. So there's obviously plenty of iron on Earth, no shortage of iron. There's also no shortage of lithium. Lithium is extremely common on Earth. It's basically everywhere. So if you have basically an iron phosphate cathode with a graphite anode, and lithium carbonate, there's enough of that on Earth to power many civilizations. Several, or easily order of magnitude larger civilization than ourselves could be powered with the battery materials that are readily available. So I don't want to suggest complacency here, but just that there is a very clear path to a sustainable energy future.
Okay,
That's wonderful. Elon, we just want to thank you so much. The National Academy of Sciences is so pleased to have you here with us today. Paul Worcester is a member of the Space Studies Board, and this is also the Board on Physics and Astronomy. And just thank you so much for the time and the interaction with our members and answering so many questions so graciously. I know it's past the 7 p.m. hour on the East Coast or wherever you are.
No problem. Well, thank you for the great.